So this is our last example that we can now look at briefly. And the example is telling us that a smaller fish is 3.0 meters below the surface of a pond and 2.5 meters from the bank of the pond. A man which is 2.0 meters tall stands 4.0 meters from the pond. Assuming that the side of the ponds are vertical, you should calculate the distance a man should move towards the edge of the pond before the movement becomes visible. I can really try to do some kind of sketching here, that supposing this is my pond, okay? They're saying that we have a fish is 3 meters below. So if my fish is here, the depth here for the fish is 3.0 meters below the surface of a pond. That is, I'm assuming if the pond is here in water. I mean the fish is here in the pond here, and that's the surface of the pond. And then they're telling that and it's 3 meters from the what? 2.5 meters from the bank. If the bank is here, the position of the fish, I can take an average distance here of 2.5 meters. And then they're saying that a man who is 2 meters tall stands 4 centimeters from the pond. If I'm looking at from here up to here, there is some guy here who is standing, maybe say, let me use this arrow to represent the man, and is at a distance of 4.0 meters. And they're telling us that his height is 2.0 meters. So they're saying that calculate the distance the man should move toward the edge of the pond before the movement becomes visible. That how far should he move? Okay? Maybe assuming if he moves and he comes here. At this point, should we continue moving, the fish will automatically see him. Isn't it? It becomes visible to this fish here. He should move some distance this side before this fish sees, because this fish should be seen here and then seeing him properly. So if he's to move this distance x, assuming it is that distance x, what is that x? Assuming the man moves from here up to here. After here, he shouldn't continue. The moment he continues, the head will come out and the fish will be in position of seeing him. So what is that distance x? Assuming if he's now here, that means that for the fish to see him, that means light rays will come refracted in the eyes of the fish there. Okay? So whichever way we take it, because you look at the principles, this one can be my R, this one can be my I. So this is the ray diagram that if it's here, the light rays will come here refracted in his eyes, and then the fish here directly will see him, so he shouldn't go beyond this. So if we are to solve this problem, I can call this one A, and I say applying Snell's law at A, isn't it? That means refractive index of water sin I should be equal to, this will be in air, refractive index of air sine of R. But can I get I? I will know that, but I can say sine of, I can say this is opposite and adjacent, but tan I equaling to opposite toward opposite adjacent. Tan I equaling, if I look at this triangle here, is equaling to 2.5 divided by 3.0. What is my I? So we can use our calculator and get I. and basically I'm going to say 39.8, that is equivalent to 40 degrees. This is 39.8, and I can take it as 40 degrees. Or even if you leave it like that, just no problem. So let me leave it there. And then if I come back here, you'll see refractive index of water. They say it is 1.33. Sine of the angle in water here is the 39.8. Should be equaling to refractive index of air is 1. The angle that is refracted in air is R. So my R is the sine inverse of those values there. Sine R. We're saying sine R, not just R. So we can say 1.33 sine 39.8 will give us that, and then shift sine inverse of the angles 58.4. So that is our angle of refraction here. And then if this is a theta, okay, I can say theta equaling to 90 minus 58.4. What is 90 minus 58.4? And then theta is equaling to 31.6. So I now, if I get this angle, I say 90 minus to get this angle here. So now, in that case, I will be in position of getting this adjacent for this here. If I can use another, I can be in position of getting what is this distance here. I can call it D. Isn't it? I know this one. If the guy moves up to here, his height will still remain 2 that. So I can say tan theta equaling to opposite out of D. But theta is that. That means that D is equaling to 2 out of tan 31.6, and my D will be some value. So what is 2 divided by tan of 31.6? That is 3.25. D is 3.25. My D is 3.25 meters, isn't it? So I'll say that X is supposed to be 4.0 minus 3.25. So what is 4 minus the answer? I can say 4 minus 3.25. 0.75. X 0.7. Because now after knowing this D, I know from here up there is 4. So if I know D, I want to know X. I know X plus D. Because here I'm saying that X plus D equaling to 4. That the distance from here up to here and here up to here, which is X that we're looking at, how far you should move up there, will be equaling to now this plus that, which is the 4. Because the man initially was located at a distance of 4 meters from the bank of the pond. So that means that if I get this one, I can conclude therefore the man should move 0.75 meters towards the edge of the pond for his, that is before his movement becomes visible. So this is how we can analyze this, because we looked at the guy moving from here up to here. At this point here, we are assuming that should we continue, his movement will be visible. So we are assuming he has brought his height now at this point. And now we say if he's here, how do we draw some ray diagram for the fish to see him? I will look at the rays from here. There's some kind of refraction because there's change in media. Okay? I got this angle here because I was given the depths and the distance from the pond where the fish is. You can use tan. After getting tan, apply Snell's law here. to get r. If you get r, 90 minus r, get this angle. Now if I have this angle, I can know the distance from the point up where the guy is currently is, that is d. Now after knowing d, I know from here up to here is 4, and then 4 minus d will give me the angle. So that is how the problem can be tackled.